Well, hello friends. Today we are going to work a little bit more on the purgeable memory feature in Serenity. So if you recall, we have this thing now where memory can be marked as purgeable, and then it has a volatile flag that determines if that memory is really like yours or not. And if a piece of memory is volatile, it means that the kernel can just yoink it away at any time. And so if we look at these two columns here, they inform us how much memory in a specific process is currently marked volatile and how much is non-volatile out of this purgeable memory. Of course, not all memory in a process is purgeable, but nowadays most processes tend to have some amount of purgeable memory. And the idea is that this memory is available to the kernel if the kernel wants it. Not the non-volatile memory, but the volatile memory. So if we sort here by volatile, we can see that even something like these shell processes here, they have a little bit of purgeable memory currently marked volatile in them. It's because we now also integrate the purgeable feature with malloc, so that when you free some memory using the free API, we actually go and try to make it volatile instead of just giving it back to the kernel right away. And the benefit for the application is that in case the kernel doesn't take it away, then you can just mark it non-volatile again and it's yours, which is much cheaper than deallocating and allocating new memory. You're just changing a flag instead of changing the address space. So today what we're going to do is we're going to actually teach the kernel how to steal some of this memory when needed, because currently the only way to actually trigger a purge is to run the purge command, which you'll see here that all these volatile memory, or some of it, will go away. And of course you can see some of it went away. And of course, some of it comes back right away because System Monitor, for instance, it's updating every second, and it uses 2 bitmaps for the window UI, and one of them is volatile at any given time. And so we take that away, but then a second later it updates the UI anyway, and so generates a new bitmap. So that part is not perfect, and we should look at some hysteresis or something like that. But it's still, you can see that a lot of memory disappeared here. So what I want to do today is I want to build a program that chews up memory, or like munches up memory, right? And keeps growing over time. And I want it to basically eat up all the memory in the system, and then I want to teach the kernel how to survive that situation by, instead of just panicking because it can't allocate memory, it would purge memory from some of these volatile pages here. So that's what we're going to do. Yeah, so we'll start by making the program that just eats memory. I think we'll call it Munch. That's a pretty catchy name. No, that's not what I wanted. What did I want to do? I wanted to do a meta. There we are. Jeez. Okay, so munch. What are we going to do here? I guess we can... The easiest thing to do is to just malloc. But we can also mmap. It might be a little easier to mmap because then it gives us a more understandable output. So let's see, main. If argc is 1, then let's see, byte size is going to be 1 megabyte by default, and also have a what the hell do you call it? Like a delay or interval? Why is this difficult? Like how long between each step, right? So by default, we'll do 1 second. Okay. Or maybe half a second. And otherwise, let's just get some stdlib up in here. If RC is 3. Toy. Wait, why are all these things in my, oh shit. A toy. Is a toy not here? Toy? Oh, it's right here. Okay. Arch1. Okay. I don't know what I'm doing. Usage, munch, byte size, munching, byte size. Oh, wait, what do I? DMS. Okay, and then finally we will print byte size and interval divided by 1,000. Okay, I don't know why this is so difficult today. Okay, eaten, munched. Okay, and then okay, there we go. Map failed. Return, I guess we'll return 1. Otherwise, we'll just keep going. Okay, so we have made ourselves a munching program. Now let's just test this out. And we can actually tweak the running params of it. So we run with only, say, I don't know, 60 megs of RAM. Let's see what it looks like. See, the system is not very heavy by default, as you can see. It's only 13 megs in use right now. But if we start, wait, hold on. Didn't I just make munch? Oh shit, forgot to sync. Alright, so let's bring this up, and then we'll munch. Right. we're just allocating VM. but because we never touch it, then it doesn't cost us anything. So in order to actually use the memory, we have to, or to commit to physical RAM, we have to actually touch it. So we'll have to do memset putter 0 byte size. And for that, we need string h. Okay, now let's take a look-see at here. So now this guy should be chewing up the memory, as we can see. Although the amount of available memory goes up as well, that's really bizarre. That doesn't seem right at all. What the actual heck? So it seems like we have found a problem here. But we crash eventually because we have no physical pages available. So my thinking is that we're going to have a limit here. Limit munch, oh, just call limit, and limit by default will be, how much did we munch here? We munched 40 megs. So let's say we want to munch 44 megs by default or something. Who knows? Limit is 42 megabytes. Here we'll run with no limit, so, or maybe we should have a limit. Oops. Byte size, limit, interval, okay, and then stopping at zoo. Okay, and then if limit and munched greater than limit, and all done. Okay, and then let's change the munch time a little bit to make it faster because this is going to get annoying otherwise. And then, why the heck did this number grow? That's so weird. So it's the user space physical comes from, it's this label right here, user physical pages label. And user physical allocated, user physical available. It's the number of user physical pages. Okay. I would think that this number should not change because we set it up here when we boot, when we initialize the paging data structures, and then we never touch it, as far as I can tell. So is that really the number that we're showing? User physical available. The free physical pages should be the, it's physical pages minus used. Right, but are we using it that way though? In the memory stats widget, it's physical allocated and pages available. Pages available here is physical allocated plus physical available. Well, that's not right. supposed to just be like that. So that was confusing. And then presumably it's the same for this guy. For the super physical pages, it's the same issue there. So it will keep growing because we're adding them together. But wait, why is it called super physical free? Okay, we're just fixing something up here. Let me just reply to my young sister here. Because I have to do some Christmassy family business later on today. Okay, so now we have at least changed the logic here so that we show the amount of memory available. Okay, so assuming that this all builds, which probably it does, then the next thing to start looking at is, wait, sum available. Is any of this right, I wonder? Kmalloc available. What does that even show? Is the amount free? Available. Allocated available. See, it doesn't seem right that this returns the total count rather than the actually available count. So this is wrong. We should just fix it here. Super physical pages used. And then the logic in the system monitor was correct. It's silly, but it will be hard to work on this if we can't have like the right information in the UI. So obviously we got to fix that. Okay, so the next thing that we need is, let's just verify that that it can go up and that everything looks right in the UI, and when we hit the top, then we die, you know? But of course, the purpose of today's exercise is to get to a point where we can munch more than we have available when we start, and the kernel will like clean things up to make way for us. So run munch, and it grows, grows, grows. Oh shit, we're about to hit that ceiling. And we did. So we're out of pages when we've munched this much. So how are we going to fix this? Well, we're going to fix it by purging something. And I guess we'll purge in allocate physical page. Allocate user physical page. So if we can't find a free physical page, then we get here. And this is the crash that we're seeing right now. And so we got to have a fallback here. So we can't find a page, but what if we can purge and find a page? So we've already disabled interrupts. So we need to look through for each VM object. let's see, for each VM object, VM object is purgeable. Can this thing break? Yes, it can. Okay, so if all right, let's cast it. And I guess we're gonna okay. So calling purge will give us back how many pages were purged. So I think we're going to do that right now. So if purging this VM object returns a non-zero value, it means it was able to free up at least one page, possibly more. And so if we're able to do that, I'll say kprintf purge saved the day. Stole the pages from VM object, something like that. Purge count. We don't have to say stole, but purged. Purged page count and purgeable VM object. Okay, now after this, we should be able to succeed with this whole thing, but so we should be able to call find physical free user physical page once again here, and this time it will work. Assert page, otherwise something is completely wrong, and then we'll return break. And here, if still no page, then we panic. Otherwise, we'll continue because purging has saved the day. So let's see how this works in practice. So I'll bring this up. Don't have terribly huge amounts of volatile memory, but there is some. Taskbar has quite a bit, for instance. So pretty much should at least see some purges, even if we fail. Damn it. Oh, interrupts disable when trying to take lock. We can't lock. We can't purge because we need to lock first. Well, that's not good. Purgeable VM object. So if one of these is locked, maybe we will have to skip over it, but I'm just thinking, can we check if it's locked? I guess we could. How would we do that? So we would just check if there's a holder. let's see. And then we can have a special version of purge that you can call while interrupts are disabled. Purge impl. This will be purge impl actually. And then the normal purge will do this. And who is this memory manager calling here, right? Yeah. So I think maybe we'll have something like purge with interrupts disabled. We should probably find a better design for this. Maybe locks, maybe like a mutex is not the right solution here, but we should use something else like a semaphore or something. I'm not quite sure. But because I think you can, if you use a semaphore, then it's easier to do stuff with interrupts disabled. But I'm not sure. I haven't really looked closely at it. But for now, we can do this. So purgeable VM object. Then this is actually purged with interrupts disabled, and we don't need impl. Or actually, we do need impl because of the batch. Purge impl, assert interrupts disabled. If paging lock is locked, return 0. Okay, so if somebody's holding the paging lock for this VM object, we will just not purge. So, you know, sucks for you, but it's unfortunate that you got a out-of-memory condition while interrupts are disabled. I mean, that's actually always going to be the case, but it's unfortunate that you got an out-of-memory condition while a purgeable VM object was locked, but it's not cool of us to take away the memory while it's locked, because that means that somebody's doing something to it. Purge impl. I guess we should return purge impl, actually. Okay, just build faster. Oh, one file left. So, can we get some munching going on? Munchy. Still trying to, oh shit, I forgot to call the right API. Memory manager. We need to call purge with interrupts disabled. Alright, come here you. Okay, we did a bunch of purging. Whole bunch of it. So these are cases where we would have panicked otherwise, but then of course we're unable to keep it up all the way. So we'll still run out of pages in the end, but we get a little bit farther, which is cool. So So this is essentially, this is essentially the right behavior. It's just that now the program is, we're not going to solve every possible out-of-memory condition today, right? But this one we can. We just have to make a better test for it, really. So let's make a separate program that's making a big allocation like that and not doing anything with it. Actually, we can test that out by we give ourselves a little bit more memory, like 64 megs or whatever, and this should allow us to complete munch, by the way, if we have 64. So munch should exit, yeah, turn back to normal. But in this situation, what if we made a really big window, right? Like, quite large. File manager. He now has 4 megabytes of volatile memory. And it's probably a bit too big, actually. But how much memory is available? It doesn't actually say anywhere how much is available. Maybe we should have some UI for that. But save 32 megs, right? So we can say munch 34 megs, and we should be able to get there by nuking the file manager's volatile memory. So what would be the arguments for that? Byte size limit interval, right? So 1 meg, quite often, and oh wait, byte size limit interval. So the limit should be 34. So 3, 5, 6, 5, 1, 5, 8, 4. Damn it. Oh, crap. It's supposed to be a 4 here. Can we trick it? No. Alright. We're gonna need to rebuild that. Of course, you know, something else that would be good is if we would kill some random process, or not a random process, we would kill the best process when this condition happens, like an killer. But that's not what we're doing today. Today we're just interested in stealing some purgeable memory to get ourselves out of a sticky situation. So now we have, file manager has 6 megs to give us. And we have 33,616. This is how much we can allocate, but we can get 6 megs on top of that. So say that we can get 6,000 on top. So we should be able to allocate 28 megs comfortably, right? So let's say 28. So munch 1 meg up to 28 megs this often. Shit, it worked. Look at that. So we allocated all the way up here, and then the kernel had to purge a bunch to allow us to keep going, but it actually worked. So this, I guess, was the file manager thing. We can look here and see what was taken, actually. Yeah, you can see file manager had his volatile memory taken away. So this is really neat. This means that the kernel is now able to take memory when we run out of memory. So running out of memory is not immediately fatal, but rather we have one backdoor to get a little bit more memory. So that's really cool. And of course, this means that we don't have to start killing anyone yet, which is something I would like to avoid for as long as possible. Although I don't want to swap the disk, because I think it's not appropriate for a modern system to be swapping to disk. It's kind of stinky. But instead, it's this kind of feature where we let user space and the kernel communicate with each other about intent, and user space can go and like allocate lots of memory, but it has a mechanism to tell the kernel what it's doing with that memory. Like, oh, don't worry, this is a cache. You can take it if you need it. I'll be fine. This is extremely valuable information. And of course, we should check that file manager comes back up. Normally, if we just start interacting with it, which it does, now he has a bunch of volatile memory again, right? And we could repeat the process if we wanted to. See that graph going up and going back down. This time we didn't have to purge anything. I guess because we started from a bit lower this time. So now we actually had, can you do something like this? Yes, you can. 29,468. Wait, what? So let's just allocate one more megabyte. I guess that's not going to do much. Wait a minute. Oh, wait, that didn't work out right. And now we crashed because we went too far. Crap. Well, you get the idea. 333. How much is that even? It's about a meg. Well, so see, I guess the issue now is that here we actually purged the file manager backing store, got back down to this level, and then when we tried to go back up, there were no longer these 6 megs. So it's obviously it's still very rickety here, but the basic mechanism works, so that I'm very happy with. So let's see, git commit lock. Kernel add lock is locked. And let's say file system procfs, fix inconsistent. Which file was that in even? It was in memstat. Listing the total number of available user super pages as the number of available pages. Total number of is interpreted in the system monitor program and displayed from in the GUI. The okay. And then we have the memory manager change. So when we try to allocate a physical page for user space, we try to purge if we can't find a page, and then try again if we purge something. It's simple, but it's very, very cool. So I think I'm gonna commit that. kernel. When user physical page allocation fails, try to purge something. Purge, try to purge physical page allocation. I'm trying to purge something. Okay, so we now try instead of panicking, we now try to find a purgeable VM object with some volatile pages to take volatile pages in it. If we find one, we purge that entire object and steal one of its pages. This makes it possible for the kernel to keep going instead of dying. Very cool. Very cool. That is very cool. This makes me realize that it would be very nice if, when you minimize a program, then we would make all of the bitmaps in that program be volatile, because right now there's absolutely no paint events going to this window because paint events are prevented when you're minimized, but there's also really no need for you to hold on to your bitmap if you're minimized. At least, I mean, you can keep it, but if we need it more than you do, then we can just take it from you. I think that would be really cool. So let's make that happen. So how would we do that? That will be in the set minimized. Oh, wait, we should commit the munch utility. Munch, add a simple user-line program for chewing up lots of memory. Okay, now when we minimize something, set minimized, what do we do then? Notify minimization state changed, okay? And then we tell all of the window management processes, but we should, if we told the, so currently programs don't learn that they become minimized. Only window managers learn it. So like the taskbar is a window manager, for instance. You can have many window manager processes. The taskbar is just one. But we don't tell the program itself that one of his windows has become minimized. So we could do that. Post message, window client. We'll define a message for this. So it'll be something like, we have window activated, window deactivated. How about window minimized? Or window, yeah, window state changed. Window ID bool minimized, something like that. And it's an async message. Okay. And we can just say window state changed, window ID, and window is minimized. Okay, so now we'll tell the program. And of course, this means that we have to update the Windows Server connection object, because it will now get this message here, so like that. No, not handshake. Handle, const, window, client, window, state changed, message. So if we can find this window in our window set, then this will send him a message. So we'll post an event on the event loop to the window, and it will be a G window state changed event, maybe something like that. Or actually, we don't even need to make an event. We can just say window did notify state changed. Message is message minimized. Okay. That's a little bit simpler, because then we don't need to go through the event loop just to tell you that your window got minimized. We can just let you know right away. We should take a batch here though, just to, so that nobody else calls this. So notify state changed batch Windows Server connection. Pool minimized. Okay, so now that we get this pool minimized, we're not tracking that. We don't need to track that, but if minimized, we can say we want to make both of our backing stores volatile. So currently we call back bitmap shared buffer set volatile, and that's what we normally do. So we could do something here where we like, if front bitmap, if we have a front bitmap, which I assume that we do, if minimized, and we should only do this if double buffering is enabled, actually. Or, well, it's probably okay to do it otherwise also. Because if you minimize a program, we don't need to hold on to the UI of that program, like the bitmap of the UI. It's just not necessary. So set volatile. And let's see, so if we have a front bitmap and if set non-volatile returns false, that means that the memory was taken away from us. It was purged while we were volatile. So in that case, we can just throw away the bitmap. And I think it will be automatically recreated. Front bitmap. Yeah, for instance, when we hide a window, we just throw away the bitmap like this. We'll have a couple of rebuilds, or just relinks because of this, I think. Oh crap, I had to redo the Windows server, but it wasn't so bad. Build system, JCS has been working on the build system lately, in the last couple of days, and it's been really interesting. A lot of improvements to dependency tracking, but it's still not perfect because now it's a little overeager, like we're building a little too much. And also parallelism is a bit broken. Because it used to be possible to just say, hey, spawn like 8 parallel jobs and then build in parallel, and I can't really do that anymore because they all try to build the same thing in parallel. They all try to like build the same dependency like libc or libgui, because all those jobs discover, hey, I don't have libc, I need libc, so I'm going to build libc, and they all do it at the same time. So it's not perfect. But it is interesting to have progress in this area. It is making me wonder a little bit if something like CMake would be the solution to all of these issues. But right now, it's nice to use raw make files because it's very understandable. Anyways, so does this work now? If we minimize the terminal, can we see him right here? Okay, so if we minimize him, all of this memory should become volatile. That didn't do anything. All right. That didn't do anything. Did you even learn that you became minimized? Volatile, poop. Okay, so this guy did it. He moved everything over. How did that work? So check out. When you minimize File Manager, then both the back and the front buffer of the UI are now volatile. That's really neat. So probably in Terminal, I know Terminal doesn't use double buffering, so maybe the logic there was broken. Maybe I think that we're always using the front bitmap, but maybe with double buffering, we're always using the back bitmap. That's probably how that works, actually. If no back bitmap, yeah, we're always using the back bitmap, and then the front bitmap is a double buffering concept. So let's see. Bitmap. Double buffering enabled. If double buffering is enabled, then we care about the front bitmap. Otherwise, we'll make a comment about this. Minimization means we can mark the front bitmap volatile in addition to the back bitmap. When double buffering is disabled, there is only the back bitmap, which we can now mark volatile. So I guess we'll say if no bitmap return. Bitmap shared buffer set volatile. I feel like graphics bitmap set volatile. Oh, right. So this is a bit confusing actually. So I should probably do something about this API. But so graphics bitmap has its own volatile API, but it doesn't work if the underlying memory is a shared buffer. Then you have to go directly to the shared buffer like we were doing in gwindow here. Anyways, let's see if this fixes the issue with terminal. So here's terminal. It has 856K of non-volatile, and look at that. It's now volatile. And totally works. Wait, when you bring it back up? Yeah, right. That's so cool. So that means that if we make this gigantic window, wait, I want to make it bigger, bigger, bigger. Oh, shit. That was too big. Oh, we ran out of supervisor physical pages. That one is harder. We can't really solve that one right now because supervisor physical pages are identity mapped, and we don't have a way to get more of those. And super physical pages are used for page tables. So I was just growing the address space too much here. But this is really neat. So let's restrain ourselves a little bit here and see that we managed to produce, 10 megs of bitmap, I guess, a little bit more. Okay, so that's a fair amount of memory, 28 megs physical. And if we minimize this, it's all volatile. Look at that. So if we purge right now, it will just nuke so much memory. So this graph here, poof, look at that. Totally purged all of the file manager. File manager went down to 1.5 megs memory usage from purging. So that's really cool. We bring it back up, and of course it starts using memory again, but that's to be expected. So this drastically reduces the effective impact of minimized programs. It's pretty cool, right? Because this means that now the kernel is able to take all of that bitmap memory from a minimized program. This is going places, I can tell. All right, so look at how many pages we were able to purge here. Then we make a tiny little dent, but then it just gets reallocated. So that's the frickin' system monitor. System monitor bitmaps. Very, very cool. I wonder if this works with something like Quake. Oh, can't even start Quake because no super physical pages. That makes sense. I just want to see, like, if we minimize Quake. Oh shit, that did not work. I think maybe Quake doesn't like this because we've given out the bitmap to SDL. Probably. What the heck happened there? Pump events. Oh, wait. Maybe Quake needs to be rebuilt. Let's just see if it needs to be rebuilt. Because of the change in the Windows Server protocol, because we're now sending that message that the Windows state changed. Because I was thinking maybe we give out that window to SDL, and then he takes like a pointer to it or something, but I don't think we do that. Come on now. Okay, there we go. Sync and run. Quake, and let's minimize you. Okay, we did. So how much memory are you using now, Quake Arena? We got Quake right here. We got a bunch of non-volatile memory. What's some volatile? Does it change when we bring it back up? Got volatile, 128, bring it down. 1 meg, okay. Fair enough. So, I mean, it's a small amount in the total scheme of things here because he's got 30 megs. What if we purge while it's running? I didn't even have enough memory to bring up a frickin' terminal. Okay, so things need work. We can purge while it's running, can we purge while it's minimized? And still keeps running. Okay. So I think we're gonna commit this. So Windows now get notified when their state changes, which is minimized yes or no. Windows server connection in the client process tells the window. And in the window manager, if a window has a client, then we post a message to the client when we change the minimization state, which is say whether or not he's minimized. And here's that IPC message. So this is pretty simple, but really nice. libgui plus Windows Server. Mark minimized Windows make. Mark minimized backing stores as volatile. Windows Server will now send out a window state changed message to clients when one of their windows is minimized. This is then forwarded to the G window, which will try to mark its underlying window backing store as volatile. This effectively allows the kernel to steal memory used by minimized Windows in case it starts running low on memory. Very cool. This is very cool. I really like this. Alright, so I guess it's a bit tricky to see this with, I can't mess with System Monitor itself, but let's do something like, let's bring up the browser, why not? Browser and grow him quite a bit here. Zoot, look at all that memory. So much of it. 23 megs physical. Oof. Then we minimize it and look at all of it. All over in that column there of the purgeable volatile. Boom. The browser was just reduced to 1.8 megs despite being huge. And we can actually interact with it in the taskbar. It doesn't affect it. It's only once we bring it up on screen, it pops back into using memory. I love it. Love it, love it, love it. That's so cool. It's the future, boys and girls. Okay, so I think this is going to be it for today's video. If you made it this far, then thank you for watching. I hope you saw something interesting. I hope you like memory usage, because it's something I like, so probably gonna see more of this type of stuff. Now, I hope you're having a good holiday. Mine's going pretty okay so far, and just gonna keep on holidaying for a while. But now I have to go and have Swedish fika with my little sister. So wish you all a great day, and I will see you next time. Bye.